So,
we're approaching the midway point of the program, and we're going to start mixing up research talks with lectures. So before lunch, 4 research talks, idea of a 25-minute presentation plus 5 minutes for questions and discussions after each one, and then going back to the final lectures by Kostas and Mitat today afternoon. But the first research talk of this morning, this day in this program is coming from Rich Brower, former PhD advisor at Boston University.
yes,
Who will
right.
tell us about,
and a star student. I mean, we need more of you. Can you bring them in from England?
tell us about a long-term project that's been going on, putting lattice field theory on curved manifolds.
Yes, okay. So I start off with just a simulation, which is a flat manifold, but I thought it'd be fun to mention that we're doing icing and 5-4-3. You always do simple things, right? And those have cluster algorithms, and cluster algorithms are incredibly fast compared to normal Monte Carlo. We can talk about it. It's not really my talk to tell you exactly how it works, but this is the local algorithm where each spin is being visited and looks at its neighbors, and it tries to agree with its neighbors. You know, the Republicans agree with the Republicans and the Democrats with the Democrats some of the time. And then, but probably not too visible, but what it really does is just move contours around. And almost every algorithm has that thing. It has a diffusive slowing down, okay? It's called critical slowing down. But in this special case, there's a clever algorithm by Wolf, which actually looks at a whole cluster and flips the cluster. And it's really quite amazing because it defines by percolation a cluster which is exactly the size of the correlation length. So it's almost an algorithm that solves the theory. It knows the correlation length. And a version of this works for 5-4 theory done by a student of mine a long time ago, Tamayo. So we can do it for both 5-4 theory and the icing model, and you know that they're the same theory. So it's good to think. So anyway, that's just a fun thing, but that's the reason we can get data of millions and millions of configurations, okay? So the point is that that means that the icing model, which is everybody's test toy, is something which we can get extremely accurate answers for. And that means that when we try to put these on curved manifolds, if it doesn't work, it means, particularly for 2D, we know the exact answer, right? If we don't get the exact answer, we've made a mistake. It's always good to have something to know when you make a mistake, and we do make mistakes. So let me describe. So the issue here is, the hope is that we can take any field theory that people have devised methods in flat space and lift them into curved space. So the question is, can you do that? And we're working on it and gradually learning the game. And it's hard, but the game that I'm beginning to understand gradually is that you have to think geometrically about the problem. After all, a manifold has curvature, has a metric tensor and so on. It's not so surprising one should think that way, but I'm only gradually thinking that way. And so I'll wave my hands about the geometry because it's really hard to get it otherwise. If we have time over the weekend when everybody has a beer or something that's relaxed, we can wave our hands and talk about the geometry. I spent the summer learning projective geometry, and it's a lot of fun. And I think it may be relevant. Okay, so as I say, the goal I've already stated is that is to see whether essentially any field theory that you can put on a lattice can be also put on a curved one. That doesn't mean I'm going to solve problems that have not been solved, like sign problems or chiral theories can't be. There's something that can't be put in flat space. I don't expect to be able to do that. That means I have to invent some other tricks, but I hope that everything that you have done on a flat manifold can be done on a curved manifold. It's not as easy as it sounds. One good news is we do know perturbatively, essentially, that any renormalizable theory in flat space is renormalizable in curved space. So at least at the perturbative level, they exist. It's not a fantasy. Okay. So anyway, now on the other hand, this grand goal, David Hilbert is very wise and says lots of interesting things, says what we should all learn, and that is the art of doing mathematics or physics. He does physics, consists in finding the special case which contains the germ of generality. And what we've done is actually gone from what we thought was a simple one, and we descend to simpler and simpler. And the simpler it gets, the more we learn, okay? Eventually, we'll get back to it. So very simple cases we take. This week, I don't think we were inspired by this, but Carty said in 85 that we could put things on radial quantization in curved manifolds if you could only figure out how to do it. He warned that it's very difficult when you go to a radial quantization. above 2 because the cross section is a sphere. So he only suggested doing it in 1 dimension, 2 dimensions, where the cross section is a torus. And it works. He actually didn't do the simulation. He did an analytic thing. And then he says, whether this will provide a useful numerical approach to critical estimate remains to be seen. And that's what I'm trying to get to. So anyway, that's the problem. And here's the whole list of things. And it's really only just to see, we started off doing the real problem we wanted, 3-dimension arc across a sphere. And then it didn't work. And in fact, we got rejected first by Carty. And then I explained to him that we weren't finishing the problem and he accepted it. And then we flipped from the IC model to 5-4 theory because it's a more field-like theory formulation. Then we went down and only looked at the sphere and not the cylinder, getting simpler. We had a little diversion into ADS space with my colleagues, which is sort of more of the same kind of technology. It's after all curved manifold. And then we finally got back to our sphere and got some real data. I'll show you. Finally, I went back to the torus and flat space with a slightly different lattice, as I said, and tried to learn lessons in something which is simple enough that I think I can lift back up to the curved space. And the notion is very simple. That is to say, every smooth manifold is flat in the tangent plane. So if we can solve something in a flat space and move the solution adiabatically around the tangent plane, we believe we can do things that are non-perturbative in terms of countertransfer. We'll see. Okay, so that's the story. Okay, I don't have to really tell you this. Weyl transforms can take flat space into curved manifolds. These are these examples. You can do all, the simple examples are constant curvature, either positive or negative. Now, okay, so here's the theory. So this is the standard diagram that I think Anna wrote. There's an ultraviolet fixed point, which when you turn off the coupling is a free conformal theory. And free conformal theories actually are differential equations, and they're solved by finite elements. So all free conformal theories you can put on curved manifolds because finite elements do differential equations, and they're really hidden. It's a Gaussian theory. It's really, but when you climb up here, you end up getting over to the Wilson-Fisher fixed point, which is actually the attractive fixed point on the critical surface. And there, of course, it's a highly nonlinear theory. And so the story is that we find counter terms in perturbation theory. And I think we have to be close in the starting point. You flow up to that. We have to be close to that perturbative limit with those counter terms. We're trying to get non-perturbative counter terms. Now, of course, Ising model is supposed to sort of magically go to the same fixed point. It doesn't really have a UV form, but by universality, it's sort of the same theory. Okay, so that's our one toy problem. I'd say, okay, so now the thing which you can write down the classical theory, of course, in the curved space, putting in the appropriate G mu nus in the right place. That's the 5-4 theory. So the question is how to recognize that on the lattice. And you need to do two things. You need to make the metric tensor into a piecewise constant space. That's actually very close to what you do in Reggie calculus. You try to metricize, discretize the metric, but then you also need to discretize the field. So there's a two-step process. And if, interestingly enough, the approximation that makes sense is to use piecewise linear metrics for G mu nu field, but it's static. We're not doing gravity yet. And we use actually piecewise constant fields. You put them together and then you get a Lagrangian, and you have to find the magic weights. And as I say, finite elements will tell you precisely the weights to use for the classical equations. We call this thing quantum finite elements because they are not the right Lagrangian when you quantize it, okay? And that's the hard part, okay? So anyway, all right, so, oh yeah, here's a quiz. How many triangles are there? This is a quiz, okay? So I have a triangle like this. And how many different triangles are there? Number of continuous parameters to describe a triangle. Someone tell me in 2 dimensions. I'll do it for you, okay? So if you're Descartes, you have an XY coordinate for each thing. So you have 2 times 3 equals 6 real parameters, right? But Euclid is not so stupid. Euclid takes out Poincare invariance, lets you move the thing and rotate it. So it says that no, there's only 3 triangles if you're Euclid. And actually, Euclid is even smarter. He also uses similarity. That's called scaling. He was a conformal field theorist. And he says, really, all you have to do is take two angles. And so he reduces it to 2. But now, if you get to be into projective geometry, you actually allow yourself to stretch the thing with affine transformations. There are 6 affine transformations, and that equals exactly the number of parameters that you started with. So actually, there's only one triangle in the world under affine transformations. And that's what to use in finite elements. That's a primitive simplex. And that's true in any dimension. The next dimension up is a tetrahedron. And it's going to have, again, d plus, it's now d equals 3. There's 4 points. And you'll find, again, that it's interesting. Exactly half the parameters are Poincare invariants, and half the parameters are affine. That means that you can take this object, move it wherever you want, rotate it, and then unrotate. And it turns out that the resultant parameters that you don't have, the interesting parameters that give you the shape are actually the singular values. The singular values tells the size of it, and it's how oblong it is. So that's the thing you want to look at to see if your triangulation or tetraization is sort of nice, okay? So anyway, that's the issue. Now, I'm going to, I'm already going pretty fast. I'm going to show you that we get some results, but then I want to get back to this affine transformation because that's sort of the new insight that we have, okay? So here's the finite elements. I cannot tell you how to do it. You can imagine that how it's done in these piecewise things. The field itself on a triangular lattice, a one-dimensional simplicial lattice, a one-dimensional finite elements is called the trapezoidal rule, right? Linear finite elements, you take spaces, you draw lines, and you get finite elements. One dimension, we've all done it. Trapezoidal. If you have a triangle, it looks like a roof that's sort of tilted, and the linear element is just that tilted roof. You do the tilted roof everywhere, and that's the first order linear element. So this is just a multi-dimensional version of the trapezoidal rule. And that means you can compute the Lagrangian. What you do is you go to Lagrangian, take derivatives. Derivatives are simple, a linear function is a constant. It all turns into a sum. So you get the weight that you get for the Lagrangian that way. The interesting thing is that when you get that weight, you usually get this crazy looking equation here. The weight of the edge of a Laplace operator has these differences of the lengths. And people get very bent out of shape in the finite element community. They realize that that length can be negative, you get them a negative weight, when the circumcenter goes out of the triangle. And they get bent out of shape and they say, this is terrible. It turns out it's not terrible. So first of all, because it came from a Lagrangian, which was positive definite, and in this case is equivalent, it could never have a negative sign when you look at all of the variables on the edge. So it's always positive definite. And I don't know why people aren't aware of this. So they say, oh, be very careful, don't get any right angles. It's not, things are not going to work. It's completely false, okay? Now, it is interesting, however, that the right-hand side is what's called discrete exterior calculus, where you take the ratio of the length into the circumcenter and the length along the bond. And you see what you're doing, you're dividing up the piece of that triangle where each bond owns the right amount. That's a perfect amount to get a good Laplacian. And it's equivalent. And it's more geometrical. And in 2D, linear elements and discrete exterior calculus is identical, but not in 3D. I couldn't find anywhere in the literature it said this. I finally had to write it down, okay? So it's just an accident that in 2D, these linear spaces are the same as discrete exterior calculus, but discrete exterior calculus has a really wonderful geometric meaning. In fact, T.D. Lee and Norman Christ and Fehrenberg actually got all the discrete exterior calculus by hook or crook. So anyway, it's, I think, the preferred way. But in 3D, you're not guaranteed its positivity, but it's good enough. And in fact, it works. Okay. So anyway, now we go to the sphere. The time goes very fast. Okay. Now, the whole point of this thing is the way we did the sphere in our original calculations is we start with the most symmetric regular triangulation, which is called the icosahedron. It's the most refined Platonic solid. And then we took all of the edges and made them into flat triangles. But that's not a sphere. Then you sit in the middle and you blow them up. And now you see all the triangles get slightly mushed. I mean, it looks pretty good, okay? But if the triangles are very, very small, then they sit close to the tangent plane. And as you go to the continuum limit, that projection of that angle is exactly an affine transformation. So locally, as you go to the continuum limit, this is what we just finally got into our brain, that in fact, locally, the thing becomes an affine transformation of a regular lattice up to order A squared. So the problem of trying to get a uniform cutoff, see the length of the edge is a cutoff, is to try to follow the discretization through the affine transformation, because otherwise you have different schemes on each point, and therefore the ultraviolet cutoff is in disagreement. And when the ultraviolet divergences kick in, it doesn't know what scheme to do, and it doesn't work. So here's what happens. Okay, all right, I'm sorry, I got slightly ahead of my story. This is the Laplacian. This shows what finite, this is classical. This is the thing if you use equal weights to the bonds, which is wrong, but if you use a slick one, the Laplacian becomes 2L plus 1. It's basically perfect. So that shows the classical equation. Maybe you see a little defect up there. Now, what happens, however, when you add the interactions is you discover that if you use finite elements, it is not a sphere. The average value of phi squared, for example, is this lumpy thing. And you see the icosahedron breathing through this thing. And it's because these triangles are changing their shape and size. So the real problem here is renormalization. But it's renormalization pointwise. But if you don't have a scheme that is a few parameters, you fail, because you don't want to have an infinite number of parameters to get to the theory, right? So you have to boil this down to a finite set of parameters. Our first way to do it, you'll have to see this is really the numerical calculation of the one loop diagram. So our first way to do it was to say all of the problems at the ultraviolet come from the divergent diagrams. So we calculate the divergent diagrams, we subtract the universal log, and we look at the variation, and then we change our action, not finite elements. And that works. And we get data. This is the two-dimensional Ising model. I won't bore you with it, but it's extremely good. The central charge is basically a half. This is not a heroic calculation, by the way. This is quite easy. But you can also do 4-point functions. Here's a map of the 4-point function, which we can compare with a bootstrap, and it looks very much like their map of the 4-point function. Okay, fine. Now we get back to the issue of affine transformations. So finally, my really bright student, Evan Owen, and I started to think about the model of an affine transformation, and we asked ourselves what it was. I don't know what order we discovered this, actually, but we said, let's look at the triangular lattice. It's a common thing to do with 3 different couplings. And if you think about it, that's at least in one-to-one relationship with the dynamics that you want to get to. But the crucial thing is when you write down a lattice action, you are writing it on a graph. You do not know the geometry, okay? This is fundamental, but people don't worry about it too much in regular lattices because they are sure they know the geometry, okay? But it turns out this Ising model wants to have a geometry on its critical surface, and you have to find it. You have to ask what it looks like in terms of lengths. So if you think of this thing as having equal lengths with these Ks, it's not the conformal theory. It's the conformal theory on an affine transformation. So it doesn't have circular correlations. It's got elliptical correlations because affine transformations take circles into ellipses. Unlike conformal transformations, which take circles into circles and keep angles fixed, affine transformations take circles into ellipses and keep parallels fixed. So the extension in the affine place of a Poincare invariant theory is going off of conformal field theory. It's actually in 2 dimensions, they're both 6-parameter groups. Actually, in higher dimensions, they're more affine transformations than conformal transformations. But so one of the problems basically is you're being forced into the wrong space by the discretization than conformal field theory wants. So that's my, sort of vision. Okay, so now it turns out we solved this problem because the Ising model is soluble. I think this is a new result. If this is a new result for the Ising model, it's kind of interesting because it's been around for a long time. So the answer is that if you want to look at the dynamics and ask what lengths should you assign to those edges so that in that coordinate system, It is the conformal theory. This is the answer. The coupling constants, K1, K2, 3, on the critical surface are the ratio of this length and the dual length that I described before. Exactly the same geometry, but it's not the same. This is the free theory. So the free theory, this is finite elements, okay? This is the non-perturbative, strong coupling geometry of the IC model, okay? It knows what it wants to be, and it's very different because cinches are not equal to 2K. The Ks aren't small, by the way. They have to go to a critical surface. They're order beta critical, right? So there's no expansion here. So that's totally non-perturbative physics. This is free conformal field theory. But you see, geometry has sort of not been lost. They both think geometrically, yeah, but they have a different notion. Okay, so anyway, we believe that this is a way forward. In order to prove this, there's a wonderful technology. It's the star triangle relationship. You work on a hexagonal lattice, which is dual to this triangular lattice. You can decimate. So if you sum out the zeros, you go from one to the other. So there's exact mapping between the two lattices. It's called the star triangle relation. Then if you get even smarter and you start with this beautiful paper of Willy Wolf, you realize that putting fermions on a hexagonal lattice is simpler than on a triangular lattice because the loop expansion always has to have an in and out. And if you have only 3 links, it goes in and out. So the loop expansion has no crossings. So it's actually very quick to write it down as a free fermion theory. Now it's a free theory. And now you can adjust the constants the way it would be for the finite element because the fermion sector is a free conformal theory. Okay? So if you go through all of this algebra, you discover those relationships. And the interesting thing is that basically what you're doing is a corner of sort of standard projective geometry. This is what Pascal would do. This is a hexagon, a particular hexagon in a ellipse. And all these beautiful theorems of projective geometry, a special case of it, is true. And what you need to do is adjust the edges of the hexagonal lattice to form a circle. And then you take these relationships, relate the triangular lattice, I'm sorry, the hexagonal lattice back to the triangular lattice, and you get these relations, okay? So it's a beautiful piece of mathematics, and we did it. Now, back to radial quantization. Well, the easiest radial quantization is the one that Carty did. Here's a linear on a torus. I just want to emphasize, I have not seen these calculations, presumably people have done them. It's incredibly accurate to put this on a torus. This is a very small laptop calculation for this critical exponent. Totally easy, right? And you could do it to higher accuracy if you wanted. So that's just a showing that radial quantization is a good idea if you can get it to work. Now you go to higher dimensions, it's harder. Oh, and the other thing, by the way, because our lattices are skewed, we can actually do exactly the right lattice for the modular space, right? We skew the thing as a torus. Then we have skewed triangles. They are these affine transformations. In fact, the modular space is the affine transformation of the triangular lattice. It can fit in perfectly. We can calculate and get the Jacobi function with all finite volume effects. So this shows that we really have the right solution. It's very accurate. We can do the modular space. Now, back to the original problem. We asked ourselves, could we use the point of view that locally, our lattice is this 3 coupling constant affine transformation. So when we go to the tangent plane, we can see the shape of all those triangles. They look very much the same. Then we adjust the bonds on those edges to be the ones that are on the critical flat space. But we do this on each piece of the tangent plane. It's varying, right? And this is a measure of spherical symmetry breaking. The red ones, it's a very small breaking, but it's one that was bothering us. So the IC model, if you don't do that careful readjustment, is the red curve, but the green curve is using this affine transformation. So actually, we think we can now do the IC model, not 5/4 theory, non-perturbatively. It doesn't have any ultraviolet fixed point in sight, and actually get the right theory on that. So we're hoping that this generalizes. And okay, let me just show you. Here's an example. This is going back to 5/4 theory. Here's an example of doing Monte Carlo with the perturbative counter terms. But notice the kind of thing you need to do. This is the Ricci curvature. Oh, sorry. Yeah, this is the Ricci curvature term. It turns out that in our tuning of constants, the Ricci curvature term is irrelevant operator, but it's extremely important irrelevant operator. And without the Ricci curvature term, when we tried to go to the continuum limit, we had to follow the green line. Since it's about the square root of a, the derivative of the square root goes singular. So it was very hard for us to convince ourselves that the answer was up there at that star without the Ricci curvature term. We put the Ricci curvature term in, and now it flattens out. This shows that you have to be very careful of what operators are appearing, even the irrelevant ones. The other one was correct, but just not very good. Then we can also go to 4-point functions. 4-point functions are done on the radial quantization. The smart thing for computer calculations, you don't want to put one of your things down at -infinity using operator state correspondence. Infinity is not a place you can go to in the lattice. So it's actually center of mass coordinates. You take a time slice and you put them at antipodal points, and then you put another one at antipodal points. And this particular configuration means that the time distance and the angular distance are directly cross ratios. Otherwise, very complicated things. But this center mass coordinates in this radial sense is the smart way to have factorization. So you get each of the cross ratios one at a time. You get it very accurately. Here's our present calculation showing that in the radial quantization, we can get a heck of a lot of states, right? These are really high states. And in lattice gauge theory, if you can get the first excited state, you go home and write a paper, right? Because it's harder, right? But this is getting the first 8 excited states. So the ability to do accurate calculations is great. But the news is so far, we wanted to see whether the central charge, which is one of the terms in the expansion, was in agreement with Bootstrap. Actually, we wanted to be disagreement with Bootstrap, but I guess for fun. But it turns out that the Bootstrap uses minimization. So this number 0.94 is the minimum allowed by the inequality of the Bootstrap. And I believe that, okay? There's not an extra assumption. This is just all of this Bootstrap things. So we are definitely out of sync with the Bootstrap at present analysis. I mean, it takes a lot of data, a lot of analysis to do it right. It could be that our statistics is not good enough. I actually think what's happening is that our counter term for lambda is not small enough, and that these two things here are probably wrong. We have to, the finer the lattice, the smaller the renormalized lambda should be. I think we need to follow a different trajectory. My personal opinion is that actually this is going to continue to go straight up, and we should have not used a independent extrapolation because we should be following the renormalized coupling. We'll see, but if I'm right, that eventually we'll get a curve that goes up and doesn't violate the bound. I don't think the Bootstrap bound is wrong. I don't know whether their C minimization is right. It's very appealing, and we're trying to check that C minimization. That's their goal. Okay, so yeah, yes.
So the C of the Bootstrap is a different thing than the central charge of the conformity theory?
No, it is a central charge. It's a ratio to the free theory. So it's actually, three-dimensional Ising model is very weak, okay? And at 4 dimensions, it has no interactions, right?
So, I mean, shouldn't the two C's be the same? Shouldn't it be the same critical theory? I'm trying to be confused.
I'm sorry. The Bootstrap says that it's this point, 0.94 with C minimization, okay? And then it says certainly it's larger than that.
Oh, sorry. You have the free 5-4. It's a free boson that you're comparing to?
Yeah,
or?
Yeah, it's just a ratio. That's all. See, actually, unfortunately, three-dimensional Ising model is pretty weakly coupled from the point of view of the central charge. No coupling is 1. It only pushes it down by 6% or something, right? The epsilon expansion has a similar statement, okay?
Okay.
But the point is that we are presently much smaller than, we're in the excluded region of the Bootstrap. So, I mean, this is, preliminary data. We have to think about it. This is a statement that I believe the inequalities of the Bootstrap very well. I don't believe C minimization, so I'd like to check it, okay? So if we could actually do this well enough, we would find out whether C minimization was just a guess or correct, okay? But we'll see. And we'll see. Okay.
Rich, I have a silly question.
Yeah.
So on this, so for your constant fit, why the error bar is much smaller than the
Oh, well,
error bars?
this is a, yeah, I actually kind of objected to this thing, but this is preliminary stuff. We're saying if there is no A dependence, then we fit it with a straight line. See, and that's plausible probably at the way we're doing the calculation at fixed bare coupling. My point is that we actually, the coupling should be proportional to, remember the coupling is dimensionful. So the renormalized coupling is the bare coupling is A times the renormalized coupling. So if I keep the renormalized coupling fixed and I go down toward the ultraviolet fixed point where I believe my counter terms, then we should be following a different trajectory. We should be not keeping it fixed as we go to A equal to 0. So that's my guess, is that we're finding a slight change, and this is a very sensitive test to that. And I'm not surprised, actually. I've been telling my collaborators that I only believe this as we go to the renormalized point. Now, this whole business of the affine transformation, the IC model, we've gotten completely out of that framework. We have a solution which doesn't rely on perturbation theory at all. So we can go back now and do this thing in the IC model with that hypothesis and not to be dependent on this counter term. In that sense, we have a non-perturbative counter term, which is remarkable that we can do it for anything, but okay, we're lucky. Okay. So
that uses up the time.
Yeah, okay. So I will use up the time by simply saying that we have looking at higher dimensions. Higher dimensions are fun. You have to look at tetrahedrons. The tetrahedron, this is the equation for the edge contribution of a tetrahedron. Nobody wrote it down, but we did. It's important because when the thing goes out of the circumcenter, all kinds of signs change. And as I said, not to worry, the signs don't cause you problems. We've also been doing this in anti-de Sitter space, same kind of philosophy. We can do dynamics there. We have this problem that's been discussed a great deal in this business, that the epsilon is sort of jagged. We have to figure out a good way to deal with that boundary condition. We actually see critical phenomena for phi-4 theory in the bulk. But since most of the bulk is on the boundary, I think this is probably really the boundary critical phenomena. You know, there's a lot of volume at the boundary. So those are just future things. And by the way, geometry is important. And Dirac came to BU to confess with Penrose that even though he never wrote down a single diagram in his papers, this is his notebook. Okay, there's a photo from his notebook. And by God, it is the geometry that we've been using. I looked at this thing, I said, oh my God, Dirac is already doing simplicial geometry, because, you know, but he didn't ever tell anybody that he was doing this, okay? And now, finally, I want to use this machine and bigger on these problems, okay? So that's the hope that we can wedge this into such a standard form that the traditional large scale thing, and remember, our government is paying for this huge facility, right? And if we can get on this facility, we have millions of dollars of support to do accurate, interesting calculations on curved manifolds. Thank you. We shouldn't let this go to waste. Let people just do boring problems on it.
Thanks very much, Rich. You've given us a lot to chew over.
Yeah.
And we will have dedicated time for questions and discussions about all of this later in the day.
But also, I mean, you know, there may be a subset, 2 or 3 people that would love to talk about the geometry more. I think it's really fun. It's very useful geometry to learn, not just for this problem. So, I mean, that's completely independent of talks, but I'd be happy to do it. I spent the summer doing it.
We have had a couple of questions. If there's an urgent one to do now, we can take it.
Yeah, the question is, did you actually do the integrals by hand, or did you do them by Mathematica when you got the
formula?
The formula. I'm trying
to
know how much.
I did that by hand, and I did that by hand. And the reason I did it by hand is that actually, I will answer this one thing. The important thing about circumcenters and simplices is that it sets up an orthogonal dual coordinate system. So in other words, it has the epsilon symbol buried in this terrible form. Because what happens, you start in a point here, and the circumcenter of a line is there, right? And then you go perpendicularly to the circumcenter of the thing. And then when you go into the tetrahedron, you go perpendicularly into the center. So this is a perfectly orthogonal coordinate system, and we know the distances are the sum of the squares. So actually, the geometry of circumcenters and simplices are beautiful. That's the reason the whole discrete calculus works. You have a concept of star to go to dual lattices. I joke with my colleagues that if you have a new idea, you should call it dual, because dual is used about 15 times in this paper. Okay, but it's only circumcentered duals that have this beautiful algebraic structure that allows you to lift continuum calculus into a discrete calculus. And it's really very pretty. So it's quite compelling that there's a geometry that you haven't lost. It's just a new one. Yeah.
Thanks, Rich. I think that's
Yeah.
a good note on which to wrap up and start.
Yeah, thanks for
setting up
letting
the
me a
next
little
talk, just in the
overtime,
interest of
but
time.
it's fun.
Thanks, Rich. Again.
Okay.